Hi everyone, I'm Mr. Fullerton and I'd like to welcome you to another special episode of the Physics in Action podcast. Today we're going to look at work and energy and do a brief review as we prepare for Regents level standardized testing. To begin with, work is a force that causes a displacement. Note in there three key words. You need a force, you need a displacement, and that force has to cause the displacement. More informally, work is really the process of moving an object. It's given by the formula work equals force times displacement times the cosine of the angle between the force and displacement. If force and displacement are in the exact same direction, that cosine theta becomes cosine 0 and that becomes 1. And then you just get work equals force times distance, and that's the formula that's on your reference table. To give you a picture of it, if we have a box and we apply a force F at some angle theta, what we're really doing when we say force times distance cosine theta is we're taking the force component that's in the same direction as the displacement. So we would have that total force F times the displacement d times the cosine of the angle theta. Note also that if you apply a force straight up, but the object moves sideways, you would do no work whatsoever. The force and the displacement have to be in the same direction. Taking a look at a sample problem from an old Regents exam, the work done in lifting an apple 1 meter near Earth's surface is approximately what? Well, I start off with my formula, work equals force times displacement times cosine theta, and I realize that the force here is just going to be the weight of the apple, mg, or in this case, I remember that an apple has a weight of approximately 1 newton. So, work becomes 1 newton times the displacement, 1 meter, and the cosine of the angle is 1. The angle itself is 0 because the force and displacement are in the same direction. So that cosine theta term goes away, it becomes 1, and you just get 1 newton times 1 meter, which is 1 joule, the unit of work. A newton meter is a joule. Can also take a look at force displacement graphs where you put force on the y-axis and displacement on the x-axis. If you have a force and displacement graph and you want to know how much work is done, you just take the area under the graph. To give you an example, if we have a force displacement or force distance graph from an old Regents exam that talks about a boy pushing his wagon at a constant speed along a level sidewalk, here's the relationship between the horizontal force exerted by the boy and the distance the wagon moves. Well, the first thing I note is if the boy's pushing it horizontally and the wagon moves horizontally, we don't need to worry about that cosine theta term. The force and displacement are in the same direction. Now we're asked, what's the total work done by the boy in pushing the wagon 4 meters? Well, with a force distance graph, to get the work done, all I need to do is take the area under the graph. So I take the area between 0 and 4 meters, which is length times width. Length of 4 meters, width of 30 newtons, 4 times 30 is 120 newton meters, or 120 joules. Taking this problem a little bit further, as the boy pushes the wagon, what happens to the wagon's energy? Well, gravitational potential energy can't change because gravitational potential energy is given by mgh, how high you are above the Earth's surface. Since our height isn't changing, gravitational potential energy can't change. Next, we talk about internal energy either increasing or decreasing, and this takes some common sense. If we do work on an object, we give it energy. So if we're giving this wagon energy, we must increase its internal energy. Another concept closely related to work is power. Power is the rate at which work is done. Its units are joules per second, which we know as the watt. And its formula is power equals work over time. But there's a little more to it than that. Since we know work is force times distance, we could say power equals work over time or force times distance over time. But if you look at the right-hand side of that term, d over t, displacement over time, is velocity. So power is also force times velocity. You can calculate it any of these ways. You can use work over time, force times distance over time, or force times velocity. They'll all give you the same answer for power. As an example, If we're asked for the average power required to raise a 1.81 times 10 to the 4 Newton elevator 12 meters in 22.5 seconds, I'm going to start off seeing that it's a power problem by writing my formula for power. Power equals work over time. Then I notice in the problem it doesn't give me the work. It does give me a force and a distance, however. So I write my power formula as force times distance over time. Now I can substitute in my numbers, and I get force of 1.81 times 10 to the 4 Newton times 12 meters divided by 22.5 seconds for a total power of 9,650 watts. Notice that watts is symbolized with the capital W. You need to be careful because capital W is also work. If you see it beside a number itself, then you're talking about units, watts. If you see it as part of a formula, capital W would be work. It can be confusing, so you need to keep track and understand what you're talking about. Let's talk a little bit about energy. All energy in the universe everywhere can be divided into two types. Kinetic, which is energy of motion, given by the formula kinetic energy is 1/2 mass times the square of the velocity, or potential energy. And there are many different kinds of potential energy. Gravitational potential energy is one kind that we've studied, where that's given by mass times acceleration due to gravity times h, the height, which is also just the work that you would need to do in order to lift something to some height above the Earth's surface. So work and energy are very closely related. When you do work on something, you give it energy, and you can get one formula from the other. But potential energy due to gravity on the surface of the Earth is equal to mgh. Another type of potential energy we've talked about is potential energy stored in a compressed or extended spring. That's given by the formula potential energy in a spring is 1/2 kx squared, where k is called the spring constant, which really tells you how stiff a spring is. Conservation of energy is one of the key points for the entire year. Energy cannot be created or destroyed. However, it can be transformed into different types. Solar energy from the sun actually starts from nuclear processes in the sun, becomes light, comes into our atmosphere, hits the ground, the plants, becomes chemical potential energy, which we then use to do work. And really, all of the energy we see on the surface of the Earth eventually started as a nuclear reaction on the sun. A good example of conservation of energy is a roller coaster. If we start off with a car at the bottom of a roller coaster, we need to do work on the car in order to get it to the top of the hill. We apply a force over some distance, and as we do that, we give it potential energy. At the top of the hill, the car now has potential energy due to gravity, mgh, because we did work on it. As it goes over the hill, it loses some of that potential energy, transforming it into kinetic energy. It loses that height and gains velocity. When it gets to the bottom of the hill, it's all kinetic energy. It doesn't have potential energy anymore, but it's going at its fastest speed. As it goes up the next smaller hill, it has some potential energy due to gravity and some kinetic energy, and so on and so on. Let's talk about springs for a minute while we're here. To compress or stretch a spring from its equilibrium position, you have to apply a force, and that's not a constant force. The force itself is given from Hooke's law, which states that the force on a spring is equal to k, some spring constant, times the distance you've stretched it from its equilibrium position, x. X isn't the actual position of the spring, it's how far you've displaced it from its equilibrium or its happy rest position. The spring constant is given in newtons per meter, where higher spring constant means stiffer springs, and the energy stored in a compressed spring can be determined from the equation potential energy of a spring is 1/2 times the spring constant times the square of the distance it's been stretched from its equilibrium position. X isn't its position, it's how far it's been stretched from its equilibrium, rest, or happy position, whatever you want to call it. Couple examples from old Regents exams. If you have an unstretched spring with a length of 10 centimeters, when it's stretched by a force of 16 newtons, its length is increased to 18 centimeters. Find the spring constant. Well, we can start off using Hooke's law, F equals kx, and we're looking for k, so we'll rearrange this to say that k equals F over x. Now we need to realize that the force is 16 newtons, but our x, our distance stretched from equilibrium, is the difference between 10 centimeters and 18 centimeters, for a total of 0.08 meters, or 8 centimeters. The distance you've stretched the spring from its equilibrium position is only 0.08 meters. Once you do that, you can do just a little bit of math and determine that the spring constant is 200 newtons per meter. Likewise, another problem, a spring with a spring constant of 4 newtons per meter is compressed by a force of 1.2 newtons. What is the total elastic potential energy stored in the spring? Well, we remember the potential energy in a compressed spring is 1/2 kx squared. As I look at this, though, I know the spring constant, but I don't know the distance from equilibrium. I don't know x. But if I use Hooke's law, F equals kx, I can solve for x and then go back to my original equation. So if I solve for x, x is force over the spring constant, or 1.2 newtons over 4 newtons per meter. My displacement from equilibrium must be 0.3 meters. Now I can take that back into my potential energy equation and say that the potential energy due to the spring is 1/2 times the spring constant, which is given, 4 newtons per meter, times x squared, or 0.3 meters squared, where I got that 0.3 meters from Hooke's law over on the right. Little bit of calculator work, and I determined the potential energy due to the spring must be 0.18 joules.